this Eduardo Pontón Memorial Lecture Series. So it's a pleasure to have Professor Chacko, and he will continue giving his second lecture on new physics beyond the standard model. Chacko, please.
All right. Okay. So before we get on to talking about models of new physics, let me talk a little bit more about constraints. So I'm going to talk about precision electroweak measurements. So what are the precision electroweak measurements? They're a set of accurate data on flavor diagonal processes involving the electroweak gauge bosons. So it consists of about a few dozen measurements, maybe 50, 60, something like that. And the point is that there are more measurements than there are parameters in the standard model. Okay, so there are more measurements than, especially, most of these measurements are related to parameters in the electroweak sector of the standard model, and there are many, many more observations than there are parameters. Okay. And so together, these measurements over-determine the parameters in the electroweak sector of the standard model. And so it becomes a powerful consistency check on the standard model, right? Because you have limited number of parameters, but they have to explain all these different measurements, right? And because of that, it also puts a powerful constraint on models of new physics, because any deviation in these measurements would indicate new physics, and if there's no deviation, you can use that to set bounds on new physics. All right. So, so the data that goes into precision electroweak is not random. Okay, so it's well-chosen data that's precise. Right, it's not chosen randomly. So here's what goes in. So you have z-pole measurements. Okay, so there were two experiments, one at SLAC and one at CERN. Okay. So the SLAC experiment was called SLC, and the CERN experiment was LEP1. And they sat on the z-pole. So they were doing E plus E minus and sitting on the z-pole. And SLC was polarized. It used polarized beams, but LEP1 was not. LEP1 was unpolarized. Anyway, they were sitting on the z-pole measurements, and they produced a lot of z bosons. So, for example, at LEP1, they made more than 10 million z bosons. So they did very, very precise measurements of the properties of the z boson. So they measured the mass of the z, the width of the z, the branching ratios of the z into quarks and leptons. They measured the forward-backward asymmetries, and also the left-right asymmetries. So this data achieved very high statistics, okay? And because they produce just so many z bosons, and it's often the most relevant for constraining new physics. So second thing which goes in is the mass of the W, which was measured at the Tevatron, at LEP, and at the LHC. And this is very accurately measured, and so it goes into the precision electroweak. Okay. So this is one of the few things that that was most accurately measured at hadron colliders, right? But the measurement is so good that it's still included in the precision electroweak. So so after running at the z-pole, there was another experiment, LEP2, which did E plus E minus scattering above the z-pole. Okay, and so that data is included. So it contains things like E plus E minus to fermions, and E plus E minus to W plus W minus, and things like that. Okay? And so that goes into the precision electroweak measurements. And lastly, there's low energy measurements from a very broad range of experiments. So the two most accurately measured are the fine structure constant and the Fermi constant, right? But there's also a lot of other data on neutrino scattering, atomic parity violation, and and many other processes. Okay? So they all go in here. And finally, actually fairly recently, what's going in is the Higgs mass and the top mass from the tevatron and the LHC. Okay? So this is the data that goes into the precision electroweak measurements. Okay? So to give you some sense of what it's all about, consider these following observables. Okay? So here's alpha measured to some ridiculous number of significant figures, right? Here's the Fermi constant, okay, measured in muon decay mostly, again to some ridiculous number of significant figures. Here's the mass of the Z, okay, and, from those 10 million events, we know the mass of the Z very, very well, to at least 4 significant figures. We know the mass of the W very well. And this is the left-right asymmetry of the electron measured at SLC. And this is the width of the Z. Okay. So these things you can see are all measured very, very precisely. Now the point is, okay, so here's what these are. Alpha is the fine structure constant measured from the anomalous magnetic moment of the electron. G Fermi is the Fermi constant obtained from muon decay. Mz and gamma Z, the mass and width of the Z measured at the Z pole. Mw is the mass of the W boson. And the left-right asymmetry of the electron is defined in this way. It's the cross-section for E plus E minus to E plus E minus at the Z pole. And the sigma L, the L means that the initial electron had left-handed polarization. And sigma R is the same cross-section when the initial electron was right-handed polarized. So now the point is this. A tree, so there are 6 parameters over there, all of them very well measured. At tree level in the standard model, these 6 observables depend only on 3 parameters. Okay? That's G, G prime, and V. That's the gauge coupling constant of SU2, U1 hypercharge, and the web of the Higgs. Okay? So these 3 parameters control all those 6 observables, right? And so that means the set of observables is overdetermined, okay, at least at tree level in the standard model. This set of observables is overdetermined, and it can be used to test the consistency of the standard model, okay, again at tree level. Okay? And this constitutes a powerful test of the standard model. And one way to check that it's a powerful test is I claim that if you were to calculate G, G prime, and V from these 3 observables, okay, using from the standard model at tree level, calculate G, G prime, and V from these 3 observables, and then use that to predict the values of these 3, every one of them would be off by more than 10 sigma. Okay, and that's telling you that these things are so precisely measured that if you don't put the loop corrections in, it will not work. Okay, so these measurements have real teeth, right? And so any beyond the standard model physics that messes up the internal consistency of all these measurements is going to be excluded, right? And when you're talking about new physics with masses that's close to the weak scale, this is often the most powerful constraint on new physics. Okay, and so you kind of have to take this into account, right? All right, so let's keep this going. All right, So when the new physics is heavy compared to the scales at which the positional electroweak measurements are made, we can integrate out the new particles and construct an effective theory, okay, in terms of just the standard model fields. Okay? So we can write an effective Lagrangian, which is the standard model plus some higher dimensional operators suppressed by the masses of the heavy new physics, right? And here these OI are higher dimensional operators composed only of the standard model fields. And usually, for most of the time, you only need to care about operators up to dimension 6. Higher, operators of even higher dimension are usually not that important. All right. Okay, so now I want to talk about the Smt parameters. So, oh, actually, before I go on, let me stop here and ask if there are any questions.
Yeah, there were a couple of questions, but I think you already answered about the left-right. What was the left-right symmetry? You already answered in detail. But some people, Chacko, are complaining about the red marker. If you can turn it off and
okay, that should be easy, right?
Yeah, and then I think they can follow your mouse. Let's see, where's your mouse? Yeah. Oh, the red marker is still there. Not anymore.
Okay, I don't know how to get rid of it. How do you get rid of this?
If you don't know how to get rid of it, it's okay. Don't bother.
Okay, how about this? Is this better?
Yeah, I think so. If people complain, I let you know.
All right. Okay.
Yeah, people are saying it's good. Okay.
All right. Okay, what else?
I don't think there are any other questions.
Okay, let's.
I think you answered the questions. Yes.
Okay, so let's keep going then. All right, so so let's talk about the S and T parameters. So there is a special class of dimension 6 operators that often arise in extensions of the standard model. Okay? And they arise in extensions of the standard model in which the new physics doesn't couple to the standard model fermions, but only to the standard model gauge fields and the Higgs doublet. Okay? So you have some new physics, it doesn't talk to the fermions at all. It only talks to the standard model gauge fields and to the Higgs, right? And when you integrate this kind of new physics out, you don't generate all possible dimension 6 operators, you generate a special class of dimension 6 operators, right? And these operators, we refer to them as universal operators, right? Or oblique operators. This is say, you often call them the oblique corrections. And because the reason is that they affect the standard model quarks and leptons indirectly, okay, in an oblique way. They affect the quarks and leptons only through the couplings of the quarks and leptons to the standard model gauge fields and the Higgs, right? So the new physics only talks to the standard model gauge fields and Higgses, and so the effect on the standard model quarks and leptons is only through, indirectly through the effect of the new physics on the Higgs and the gauge bosons, right? Okay, this doesn't work very well. Okay. All right. Okay, so let's consider the dimension 6 operators that contain only the gauge fields and Higgs fields. So these are the operators that would be generated from this kind of new physics. Now there's only one operator with 6 Higgs fields. And that's this one, H dagger H cubed. That's the only one with 6 Higgs fields. Now, coming to operators with 4 Higgs fields, there's this one and this one. Okay. And in principle, there are many other operators you can write with 4 Higgs fields, but if you can eliminate, when you're dealing with high dimensional operators, you have to choose a basis, right? Because there are field redefinitions which relate many of these operators, right? And that's equivalent to using the equations of motion, right, to rewrite some operators in terms of other operators, yeah, together with integration by parts. I know you guys had a set of lectures on effective field theory, so hopefully it was explained that how to choose a basis and how to use the equations of motion and the integration by parts to get everything into some basis. So the idea is that there are many operators with 4 Higgs fields, but you can choose these two to be independent, right? And those two form a basis, and then everything else can be, put into this form once you use the equations of motion and integration by parts. So just these two. Now, when you come to terms with 2 Higgs fields, then there's a lot. All right, there's a lot of terms with 2 Higgs fields. Most of these terms are of this form, right? Where you have something like H dagger H times a product of gauge fields, or H dagger H times this FF dual, where F could be a gluon, a W, or a B, right? But the interesting ones are the ones where these two are not the same. Okay, and there's two like that. There's one which couples this product of Higgses to a W and a B, and then there's something similar but with the dual of W. So that's W with an epsilon tensor. So so these are so these ones are particularly interesting. And now there's a whole bunch of operators that only involve the gauge fields, products of 3 or 4 gauge fields. We are not going to consider any of them, though there are. So we have listed a bunch of operators. And out of the ones we have listed, 2 of them are very tightly constrained by experiment and therefore very important, right? And they're these 2. This one I'm calling OS, and this one I'm calling OT. Okay? And here tau are the Pauli matrices. So why are these important? Okay, so let's look at the first one. If you replace H by its Web, okay, so this becomes some V squared. You can see that what you're getting is so this by itself looks like a funny kind of kinetic term. It's a kinetic term that mixes W3 with B. Okay. So I claim when you set the Higgs to its web here, you're going to get a kinetic term here that mixes W and B, right? And so that's going to induce a mixing between the photon and the Z in the standard model. Okay. And that means that the charges of what that means in practice is that you're going to end up slightly changing the charges of the Z. Okay. And yeah, the operator OT, when you set the Higgs to its web, now remember this capital D mu, it contains a gauge field. Right? And so what you'll see is that if you set the Higgs to its web, you're going to end up giving a mass to end up giving a mass to the Z. Okay? But you're going to give a mass to the Z without giving a mass to the W. Okay, and remember I told you guys yesterday that in the standard model there's a custodial SU2 symmetry, which means that the only effects which can give mass to the the only effects which split the mass of the W and the Z have to come from hypercharge or from the Yukawa couplings. But if you have new physics that generates this operator, this is going to be another source of custodial SU2 violation. Okay? And that's very constrained, right? Remember how well the mass of the W and the mass of the Z is measured, right? In that data I showed you guys a few pages ago, right? So this operator would mess up this operator violates custodial SU2, and it's going to mess up the ratio of masses of the W and Z, right? So so these two operators are very powerfully constrained. Now there are many other dimension 6 terms that you can write, and we looked at some of them. But at present, as things stand today, they are not very powerfully constrained by the data, right? And the reason for that is that when the Higgs is replaced by its web, their only effect is to alter the values of parameters that are already present in the standard model. Okay, so let's go back and look. Okay, so for example, this operator. Okay. So if you set the Higgs to its web, it does nothing. It's just a contribution to the cosmological constant, right? So yeah, so for this operator to do anything, you have to have you have to look at a process where the Higgs is dynamical. So you actually have to exchange a Higgs or have an external Higgs to see anything from this. And similarly here, right? If you set the Higgs to its web, right? This is like a correction to the kinetic term of the Higgs, right? But it's not, it's not observable unless you make the Higgs dynamical, right? So you expand the Higgs about its web, then it's going to modify the properties. It's going to affect processes which involve the propagating Higgs, right? Either on shell or off shell. But yeah, so and again, this operator, it's going to change the kinetic. If you set the Higgs to its web, it's simply going to change the kinetic terms of the F mu nu, right? But it's not going to do anything more than that. On the other hand, if you expand the Higgs about its web, this is going to do something. It's going to give a new way for the Higgs to decay into gauge bosons, right? So yeah, so in principle, yeah, things, once you allow the Higgs to fluctuate about its webs, then some of these operators can do something. And but the point is that we haven't measured the Higgs precisely enough for those to place any kinds of useful limits on those operators. Okay. So the operators that we can place useful limits on are the ones and for which when the Higgs is replaced by its Webb, it actually alters the properties of the gauge bosons or something. Okay? Now this could change, of course, right? So, eventually the LHC will make 100 million Higgs bosons, and we're going to know its properties a lot better than we do now. Okay? But as things stand, most of those operators are not constrained. All right, let me stop here and ask if there are any questions.
Yes, so there are two questions at the moment. So Sudipta asks, can you please explain why h dagger h cubed will behave as a cosmological constant when we take the VEV?
Okay, so why this behaves like a cosmological constant? Sure. So when you set the Higgs to its Webb, this is just a constant in the Lagrangian, right? And remember, when you're coupling to gravity, right, the action looks something like integral d4x times square root of minus g times L, where L is the Lagrangian. Okay, so integral d4x square root of minus g, where g contains the graviton, right, times L. So if you put a constant here in L, now you have something like d4x square root of minus g times this constant. Okay? And so if you expand the graviton about Minkowski space, so you write g mu nu is equal to eta mu nu plus h mu nu, what you'll see is this constant is going to source h mu nu. Okay, so yeah, so you're going to find that the h mu nu couples to this constant, so it acts like a source for the graviton. Okay, and that's what a cosmological constant does.
Yeah. So actually, I talked about this last week about the cosmological constant. So
Great.
exactly, yeah. So that's just a constant in the Lagrange. Just want to point out that there is also a coefficient here in all these terms, 1 over lambda squared, that makes things the right dimension.
These are all dimension 6 operators.
Yeah. So in the Lagrangian, yeah. So Sudipta got it. And Miguel is asking, could you please repeat the explanation of why the operator O sub P violates the custodial symmetry when the spontaneous symmetry breaking takes place?
So this one, you'll have the pleasure of working that out for homework. Yeah, so one of the homework problem is to show that this thing violates custodial SU2. Okay. So remember the custodial. So remember that the custodial, the standard model, it obviously has SU2 left, and the Higgs part of the potential, together with the coupling to the W bosons, respects an additional SU2, right? So that's so you have essentially, and that's where the custodial SU2 comes from. So you have two SU2s. So this one I claimed respects only the standard model SU2 plus hypercharge. Okay, so the easiest way to show that this doesn't respect custodial SU2 is to expand this out in terms of real fields, and there are 4 real fields. And so if you have the SU2 left and the custodial SU2, there should be 6 rotations you can do among these 4 fields. And what you'll find is that 2 of those rotations are not symmetries. Okay? 2 of those rotations will not be symmetries. The 4 of them which are symmetries will be the SU2 of the standard model, and one of them which is hypercharge. Okay? Those will be symmetries. So the remaining 2 will not be symmetries of this thing, and so it violates custodial SU2.
Okay. Anupan is asking how quarks get affected by those operators that do not interact directly with fermions because of loop corrections.
No, for example, for example, this operator is going to mix the Z and the photon. So what's going to happen is that, when you diagonalize the kinetic term, you're going to change the coupling of the Z to quarks. Okay. And so when you do quark-quark scattering or something through exchanging the Z, it's going to be affected because you've altered the couplings.
Okay, I don't. Sorry, go ahead.
And similarly with this OT, you're changing the relative masses of the W and the Z. And so, any process in which you exchange a W and Z boson, right, with you have external fermions and you're exchanging a W Z boson, is going to be affected.
Okay, I don't see any further questions related to the lecture, so go ahead, Chacko.
Okay, so let's keep going then. All right, so then I'm going to focus on those two operators which are powerfully constrained. So we'll consider the standard model Lagrangian to which we just add the two operators OS and OT. Now, there is a one-to-one correspondence between these two operators and what are called the Smt parameters of Peskin and Takeuchi in the basis that we are employing. So, maybe, I guess it's almost around 30 years ago now, a long time ago, Peskin and Takeuchi identified identified three parameters, S, T, and U, right, which parameterize the oblique corrections. Okay. And they were very important because they powerfully constrained theories like technical error and things like that back in the day. And they're still, so usually even today, we parameterize the corrections to positional electroweak if they are oblique in terms of the S and T parameters, right? And the way I've chosen this OS and OT, I had to choose a basis, remember. I had to choose a basis for the dimension 6 operators. And I've chosen my basis in such a way that there's a one-to-one correspondence between OS and OT and the S and T parameters of Peskin and Takeuchi. Okay. So, so in principle, if you have some new physics model which is heavy, which gives oblique corrections, and you integrate out the heavy physics and you generate, you find the coefficients of these operators, OS and OT, then you can immediately read off S and T. Okay. So if you know the coefficients AS and AT, you can read off the Peskin-Takeuchi parameters. Okay, and since if you open the PDG, right, you will see that the constraints on oblique parameters are presented in terms of the S and T parameters. You would be able to look at the bounds from the PDG and interpret them into bounds on your new model, right? So this is the relation. So if you go back historically, Peskin and Takeuchi actually introduced three parameters. There was a third parameter called U. But in theories with a light Higgs, U is actually a dimension 8 operator. And so we don't need to think about it. Now, if you're wondering why did these guys introduce a dimension 8 operator, you got to remember in those days, they didn't even know if there was a Higgs, right? They had no idea, right? And And if you don't have a light Higgs, then U is actually pretty constraining as well. But if you have a light Higgs, then there's basically nothing more you get from U. So nowadays, we know there's a light Higgs, etc. We mostly just ignore U and we present everything in terms of S and T. Okay, so now I'm just going to, so here's a plot which shows you the experimentally allowed range of S and T. Okay, so what you're seeing here, so the allowed region, sorry. Okay, so the x-axis is S, and the y-axis is T. This plot is taken from the most recent edition of the PDG. And the allowed region, okay, is this pink colored region. And the standard model, the best fit to all the standard model data is this black dot. Okay. Okay. And I'm sorry. I think the black dot is the standard model prediction. So the standard model prediction is 0 and 0. Okay. And so you can see the standard model just about squeezes into this 90% ellipse. Okay. It just about squeezes in there. And so this is the famous precision electroweak ellipse, which has killed many models of new physics, right, over the years. And I think I've given you enough information so that, in principle, if you have a model of new physics, you can integrate it out, determine the coefficients of OS and OT, right, and translate it into S and T using these formulas, and check against the precision electroweak ellipse, okay, from the PDG. Right. Of course, if you have a more complicated model which couples with the new physics couples to fermions, this is not enough. Okay, but this is almost always the starting point. Okay. If you can't, if it fails the test of the precision electroweak ellipse, you're already dead and you don't need to think further. Okay. All right, any questions before we move on?
Yes, so there are a couple of questions. So Tess is asking, in a model with a light scalar besides the Higgs, would the U parameter be relevant?
I don't think so. As once you have your light Higgs, which is giving mass to the W and Z, then I think the U will not be relevant.
Okay, and Sudipta is asking how to calculate the expressions of S and T parameters.
Okay, so what you have to do is you have your new physics. Okay, so you have some model. You integrate it out. Okay, and then you're going to get a bunch of higher dimensional operators. Okay, go to a basis where these are the go to a basis where these are kind of like the basis operators, right? And in that basis, determine the coefficients of these two operators. Okay. So in other words, find out what AS and AT are. So what those are going to depend on what your new physics model is. Okay. So when you integrate out your new physics, you'll find the coefficients of AS and AT in terms of the parameters of your new physics model. Once you know AS and AT, this is the relation between S and T and AS and AT. Okay. So theta W is the Weinberg angle, V is the Higgs wave, alpha is the fine structure constant. Okay. So this is the relation between S and T and AS and AT. And then once you know what S and T are, so that's how you get it.
Okay, and Anupa is asking, can we use any basis? For example, can we take 5-dimensional operators basis?
Okay, so okay, so there are a couple of things here. So there's two issues here. One is, so if you look at the dimension 5 operators in the standard model, I think the only one is the one which is the Weinberg operator, which gives neutrinos their masses. I don't know if there's any other dimension 5 operator in the standard model. There's definitely very few. Okay, and so for operators of any dimension, okay, you have to choose a basis, right? And so you can't choose. You can't use dimension 5 operators as a basis for dimension 6 operators. Within the dimension 6 operators, you have to choose a basis. And similarly, within the dimension 5 operators, you have to choose a basis. All right. So yeah, so you can't choose your basis. You know, there are rules for choosing a basis, which, you know, I cannot explain to you because I just don't have the time. Right. It's something that, in principle, if you you know, take a course on effective field theory or something, it'll be explained to you. Okay? So the reason I'm stressing this basis thing quite a lot is that when I say that S and T are related to AS and AT like this, that's only true in the basis I chose. Okay, if you work in a different basis, you can still have those operators, right? But they may not. That may not. You can't use this simple relation between the S and T parameters and AS and AT. Okay. So this basis was very cleverly chosen by somebody many years ago, and for precisely this reason. Okay. And so that's why I'm kind of making a big deal out of it. Okay. There are many other basis choices which are consistent and make sense and everything. The only problem with them is that you don't get this one-to-one relation between S and T and the coefficients of those operators.
Okay, Chacko. I think those were the questions. So
all right.
Move on.
Okay, so let's see. All right, so let's start on the second set of lecture notes. So now I'm going to switch gears completely. Up to now, I've mostly been talking about constraints on the standard model, et cetera, et cetera. So now let's get to hopefully the more interesting part. Let's actually start talking about some models of new physics. Now, so in my lecture yesterday, I said, generally speaking, the most interesting models are the ones which solve a problem of the standard model and which also are experimentally testable, right? And for that reason, a lot of attention has been paid to models that address the hierarchy problem, because a lot of those theories are actually, they solve a fundamental problem of the standard model and they're actually experimentally testable. Okay? So they hit both, they cross both both boxes. Right? So let's actually first talk about the hierarchy problem of the standard model. So the hierarchy problem. So the Higgs potential in the standard model takes this form. It's a Mexican hat potential. So you minimize it, and in unitary gauge, we can expand out to the Higgs in this fashion, right? And this is mostly just to set conventions, right? So my V is 246 GeV because of this factor of √2 up front. So we minimize the potential, and this is what we find for the Higgs wave, and this is what you get for the W boson mass, and this is what you get for the Higgs boson mass. Okay, so I just turn the crank, and this is what you end up with. So then, for the physical Higgs boson mass of 125 GeV and the electroweak wave of 246, we get M is about 90 GeV, and this quadratic coupling is about 0.13. Right. So these are just the numerical values of these parameters in the standard model. Oh, this page didn't come out so well. Let's see, maybe I should try to make this a bit bigger. Okay, hold on. This is not too good. All right, so let's just try to push through. I think hopefully this is the only troublesome slide. Okay, so what I'm trying to say here is that the hierarchy problem arises because the Higgs mass parameter receives quantum corrections from high scales. So the mass we observe is a sum of the bare mass plus there's a piece from the quantum correction. So in other words, this mass parameter here, okay, this mass parameter is a sum of two things. There's a contribution, there's a bare mass, and there's also a piece that comes from quantum effects, okay, loop corrections. So this M squared is the sum of the bare mass plus the quantum corrections. And the quantum corrections, the problem with the quantum corrections is that they are quadratically divergent. So they scale like lambda squared. And so, for example, there's a quantum correction from the top loop, right? But there are also quantum corrections from the gauge loop and from the Higgs self-coupling. Okay? And all these quantum corrections are quadratically divergent. And so this lambda here is some kind of an ultraviolet cutoff. And what you find is that in the case of the top loop, when this cutoff is, even if this cutoff is as low as 1.5 TeV, okay, even for a cutoff as low as 1.5 TeV, the quantum correction piece is 10 times bigger than the bare mass. Okay, and similarly, for this gauge loop, if the cutoff is as low as 3.5 TeV, then this quantum correction is 10 times bigger than the bare mass. And in the case of the Higgs self-coupling, once the cutoff is around 4 TeV, the quantum correction is 10 times bigger than the bare mass. I mean, I'm sorry, not bigger than the bare mass, 10 times bigger than the observed mass. Okay. So the quantum corrections, even for fairly low values of the cutoff, like a few TeV, okay, this quantum correction is much bigger than this observed mass, right? 10 times bigger. So that means that in order to obtain the value of the mass that we see, you need a delicate cancellation between this quantum correction piece and this bare piece. Okay, so even if the cutoff is as low as 5 TeV, because the top loop is so big, you need a few percent, a cancellation of a few percent between this quantum correction piece and this bare piece. Okay? Each of them has to be much, much bigger than the observed mass by more than an order of magnitude. All right, so let's go back to all right. So all right. So the point is that if the cutoff lambda is greater than a few TeV, the quantum corrections are much bigger than the observed mass. And the bare Higgs mass parameter has to be finely tuned against the quantum corrections to reproduce the observed value of the Higgs mass. Okay. So in other words, here are two independent parameters that as far as we know are completely independent. There's the quantum corrections, which depend on things like the top Yukawa and things like that. And this bare mass piece, which doesn't, as far as we know, depend on any of those things. And they have to be tuned against each other to a few parts in 100, you know, if the cutoff is, to at least a few parts in 100 if the cutoff is greater than a few TeV. So that seems pretty peculiar, right? It seems rather contrived and unnatural. So this is what we call the hierarchy problem or the naturalness problem of the standard model. Now I want to talk a little bit about this because it is a little bit complicated. So in framing the hierarchy problem, I used a crude kind of cutoff regulator. So one may worry, and in fact, many people worry, that the hierarchy problem is simply an artifact of this choice of regulator, right? For example, I could have done the same loop calculation using dimensional regularization. And in that case, there are no quadratic divergences at all, right? So we need so strictly speaking, we need to formulate the hierarchy problem in a way which is independent of regulator. Okay? And the way to do that is to ask a physical question. Okay? All regulators will give you the same answer if you ask a physical question. So the way to think about it is that the hierarchy problem can be seen to be independent of regulator when lambda is interpreted as a physical mass scale at which new degrees of freedom appear. So we believe that we need new physics of the Planck scale, okay? Because you know, gravity makes no sense. You can't, basically the standard model makes no sense because gravity makes no sense once you're at energies above the Planck scale. Okay? So we know you need new physics at those high energy scales. So the Planck scale is a physical mass threshold where we expect new degrees of freedom to appear. And similarly, if you think about the hypercharge gauge coupling, okay, it grows as you go up in energy. And eventually it's going to hit a Landau pole where, things become non-perturbative. Okay? And at that point, again, you're going to need some kind of new physics to describe what's going on. All right. So for these reasons, physicists believe that there has to be some kind of new physics at high scales. And what this what the hierarchy problem represents, it's telling us that the Higgs mass is incredibly sensitive to the new physics that appears at those scales. Okay? So you put in a new physics at some high scale to smooth out the behavior, the UV behavior of hypercharge. That new physics is going to feed into the Higgs mass, and it would tend to make the Higgs mass super heavy unless there's some tuned cancellation. Similarly, if there's new physics of the Planck scale, like string theory, there'll be new string states there. They are going to feed in. Okay, there are going to be new loop diagrams involving these heavy states, and those are going to feed into the Higgs mass. And they would tend to make the Higgs mass very, very, very heavy unless there's some tuned cancellation between different contributions. And the point is that whatever regulator you choose, once you have put in whatever new physics is there, whatever regulator you choose would give you the same answer. Okay? And they would all show that the Higgs mass is incredibly sensitive to this new physics. Okay? So it's in that sense that the hierarchy problem is regulator independent. Okay, so the sensitivity to new physics at scales lambda of order M Planck is what's called the big hierarchy problem, because M Planck is so much higher than the weak scale. But our calculation of the previous page shows there's a little hierarchy problem. So even if there's new physics as low as 5 TeV, even if it's that low, okay, there's still like a few percent level sensitivity. Okay. So let me talk a little bit more, and then I'll come give you a chance to ask questions. Let me proceed a little bit further. Let me talk a little bit about solutions to the hierarchy problem. So probably the best, the most well-motivated solution, and the one that's received the most attention definitely, is supersymmetry. So supersymmetry, what it is it's a symmetry that relates bosons to fermions. So for every particle in the standard model, we introduce a particle with the opposite spin. Okay. So if it's a boson, we introduce a fermion. If it's a fermion, we introduce a boson. And the point now is that the Higgs so under supersymmetry, the boson and the fermion have the same mass, right? The boson and its partner have the same mass. Then the chiral symmetry that protects the mass of the fermion superpartner of the Higgs. So fermion masses are protected by chiral symmetries. So the chiral symmetries will protect the mass of the fermion superpartner of the Higgs. Now, because the supersymmetry forces the scalar Higgs to have the same mass as its fermion partner, the mass of the fermion is protected by chiral symmetries. The Higgs mass is protected by those chiral symmetries as a consequence of supersymmetry. Okay. So this is how supersymmetry addresses the hierarchy problem. There's an extra symmetry, right, that comes in and protects the mass of the Higgs. The other approach, which has received an enormous amount of attention, is the composite Higgs approach, which is equivalent to warped extra dimensions. So in these models, the Higgs is not an elementary scalar. Okay? It's not an elementary scalar. It's not a fundamental particle. It's a composite made up of more fundamental constituents. Then there are no quadratically divergent contributions to the Higgs mass parameter from scales above the compositeness scale. So now here, if we call lambda the compositeness scale, the quadratic divergent contributions to the Higgs mass are cut off at that scale. Okay? And above that, there's no Higgs, right? It's just you just have some more fundamental constituents which may not even include scalars, right? They may just be fermions. Okay? And so the quadratically divergent contributions to the Higgs mass parameter are cut off at the compositeness scale. And if the compositeness scale is close to the weak scale, okay, the hierarchy problem is solved. All right. Now, the ADS-CFT correspondence relates composite Higgs models to solutions to the hierarchy problem based on warped extra dimensions. Okay? So there are Randall-Sundram models, which are extra dimensional models based on warped extra dimensions, and they also solve the hierarchy problem. And they are closely related to the composite Higgs ideas through this ADS-CFT correspondence. Okay. So these are the two traditional approaches to the hierarchy problem: supersymmetry and composite Higgs. Those are the two traditional approaches. Okay. Other proposals include, so they are not, there are many others. Other proposals include large extra dimensions, the anthropic ideas I talked about yesterday involving the multiverse, right? And more recently, there's a set of ideas involving something called the relaxion. Okay. So we live in an epoch of time in which the weak scale is small in the relaxion idea. So there's a bunch of other ideas out there, okay? But I'm going to focus on these two, supersymmetry and composite Higgs, especially composite Higgs, because in the last few years there's been a lot more work on composite Higgs than there has been on supersymmetry. Right? So at this point, let me stop and ask if there are questions.
Okay. So Zahid is asking, I have problems here with my. Zahid is asking, does the fine-tuning of bare mass imply that the bare mass has to be a function of the cutoff regulator and physical mass beyond which new degrees of freedom appear?
So usually you don't take the bare mass to be so when you set up the hierarchy problem, you're assuming the bare mass is independent of the cutoff, okay? And you need some amazing correlation between those independent parameters, right? To get the observed Higgs mass. Okay? That's the way you set up the hierarchy, that's the way the problem is set up. Now, to solve the problem, okay, usually what you need is, there's no easy way to solve it that anybody knows, where the cutoff is really high and there's some correlation between the cutoff, this high cutoff, and the bare mass of this high cutoff and this loop corrections. Okay? Nobody knows how to correlate them in such a way at high scales such that you end up with a very light Higgs. Okay? So usually the way people have tried to solve the problem is to have new physics at very low scales, which so that your quantum corrections are small and your bare parameter can also be small. okay, even though they're independent.
So Anupam is asking, I don't understand the question, but he's asking, in dimensional regularization, what is the structure of the quantum corrections in the Higgs mass?
So what will happen is that what will happen is, oh geez, of course, it's going to be on this page, which you can't see. All right. So here there's a lambda, which is the cutoff. Okay. If you do it with the dimensional regularization, this lambda will be replaced by the mass of some new field, okay, some new particle, which has a mass at that high threshold. Okay, so whenever you have a UV threshold, some new physics at the Planck scale, there are going to be new particles with masses of order that new threshold. Okay, so if you have a string theory at the Planck scale, there are going to be particles with mass of there are going to be particles or string states with mass of order the Planck scale. Okay, and so this lambda, the cutoff, will be replaced by the mass of the string states. Okay? And because the mass of the string states are so heavy, this will be very, very big. Okay. Now the point is that it's not. So the sensitivity to the cutoff is replaced by the sensitivity to the masses of these very, very heavy states. Okay. And you will get the same answer now whether you use dimensional regularization or you use a hard cutoff or anything. You'll find that you're not asking a physical question. How does the mass of the Higgs depend on the mass of these heavy string states? And you'll find that you get the same dependence, whatever regulator you use.
Okay, Sudipta is asking, can you talk a little bit about hypercharged gauge coupling effects? Maybe he's referring to the Landau pole.
Yeah, so if you calculate the beta function of hypercharge, what you'll find is that the hypercharged gauge coupling grows at high energies, okay? Gets bigger at high energies. And eventually it becomes non-perturbative, okay? It becomes, the coupling becomes bigger than 4 pi, alpha becomes, bigger than 1. And the coupling becomes non-perturbative. And at that point, the theory is not well defined anymore, and new physics has to come in. Okay? And so that represents the scale where that new physics comes in represents a new threshold, right?
Okay, I don't see any further questions at this point, so please go ahead. Okay.
So let's start talking about supersymmetry. Right? So weak scale supersymmetry. So weak scale supersymmetry is an attractive solution to the hierarchy problem. So let's talk a little bit about its attractive features. Now, unfortunately, in my when I scanned this, some of this writing was in different colors. Okay? And the point is, I wanted to point out the pros and the cons. All right. And the pros were in black and the cons were in blue, but unfortunately in the scan, it's come out that everything is in black, which is a bit unfortunate. Okay, so I'll try to, so it's unfortunately it doesn't look very logical, okay? But I'll try to explain it as I go through what's actually written here. So the first great thing about supersymmetry is that it solves the hierarchy problem. Okay, so that's the first great thing about it. Unfortunately, all simple models suffer from a large residual fine-tuning. Okay. So it doesn't completely solve the fine-tuning. At least simple supersymmetrical models don't. They don't completely solve the fine-tuning. And you still have to do some tuning at the level of 1 part in 100. So that's the kind of the con, right? Another great thing about supersymmetry is that in supersymmetric theories, you get unification of the strong weakened hypercharge interactions. So in supersymmetric theories, in theories with weak scale supersymmetry, there are new particles with masses of order the weak scale, and they contribute to the running of the gauge coupling constants. And if you extrapolate the gauge coupling constants based on assuming there are new supersymmetric particles with masses of order the weak scale, what you find is the coupling constants meet very nicely at some high scale. And that suggests that there could be a grand unified theory there. Okay? So that suggests that at this scale, there's some grand unified theory. And the strong, weak, and hypercharge are being unified into that grand unifying group. Okay? So very exciting. Okay? And the thing is that doesn't happen in the standard model. If you just extrapolate this, the strong, weak, and electromagnetic interactions, just assuming that there's no particle content beyond the standard model, the three coupling constants don't meet. And yeah. Okay. Now, okay, so that's the pro. So that's a very attractive feature of supersymmetry, right? Many people I know, many famous physicists you've heard of, fell in love with supersymmetry when they saw this amazing fact. So it was at LEP in the early 1990s that they first measured the coupling constants precisely enough to see that this amazing unification happens in supersymmetry. And that was the time a lot of particle physicists first fell in love with supersymmetry, because that just doesn't happen in the standard model. Okay, so that's one of the great advantages of supersymmetry. But of course, there's also some cons. One is that if you really have a grand unified theory there are going to be threshold corrections from, there are going to be new particles there with masses of order the gut scale. Okay? XY gauge bosons and Higgs triplets and things like that. And those are going to lead to corrections to this precise unification. And in practice, if you take any real model, those corrections are pretty big, okay? Usually pretty big. And so this amazing unification looks like a little bit of an accident. Okay? The unification is more precise than you would find in most real models, right? And from that point of view, the standard model doesn't look so bad. I mean, yeah, they don't meet, but the error in their not meeting, like this, the area of this triangle is not that big. In fact, it's pretty much what you might expect if you if you actually carefully put in the threshold corrections from the grand unified theory and things like that. So you could argue, well, maybe this is not so bad anyway. Right. So the third remarkable fact about supersymmetry is that it has natural dark matter candidates. Okay? There are several neutral particles that can play the role of WIMP dark matter. Right? Okay, so that's the pro. The con is that in simple models, the relic abundance does not come out easily. In other words, you usually end up with too much dark matter, okay? More than you want. And what's more is that a lot of the natural parameter space is excluded by direct and indirect detection, and also by direct searches for supersymmetry of the LHC. Okay, so yes, it looks amazing, right? It solves the hierarchy problem, it gives you unification, it gives you dark matter, right? It looks amazing, but you look in detail, you can, suppose you're a guy who doesn't like supersymmetry, and there's a lot of guys like that. These are the things they would say. Well, there's a tuning of 1 part in 100 left. Yeah, you look carefully at the unification, it's a bit too good to be true. Yeah, there's a dark matter candidate, but the relic abundance doesn't come out right, so I think so. Now here's another remarkable thing about supersymmetry. If you look at the minimal supersymmetric standard model, the top you cover flows to a fixed point. Okay? So if you start, so assume you start at some high scale with some random value of the top you cover, right? And then you run the RG. What you'll find is that at low energies, the top you cover, whatever you started from, it tends to flow towards the same value at low energies. It flows to a fixed point. And the value of the fixed point is controlled by the QCD gauge coupling. Okay. And you have this amazing fact that you can calculate what the value of the top you cover should be at the fixed point. And it's remarkably close to the value of the top, the top mass that we see. Okay, and this is a remarkable thing. It doesn't happen in the standard model. In the standard model, also the top you cover flows to a fixed point, but the value is very different from what the value that we see. Okay, so this is another remarkable thing about supersymmetry. I don't have anything bad to say about that. It's just true. Okay. The fifth remarkable thing about supersymmetry, it predicts a light Higgs in agreement with observation. Okay. For example, before 10, 20 years ago, right? We didn't know we had no idea what the value of the Higgs mass was. I mean, it could have been 300 or 400 GeV very easily. Okay, and supersymmetric theories a long time ago already predicted that the Higgs was light, okay, below 200 GeV. In fact, the supersymmetric theories wanted an even lighter Higgs below the Z mass, right? And so we actually do see a light Higgs, okay, below 200 GeV. Now, the Higgs is still somewhat heavier than you would naively expect from supersymmetry. Supersymmetry would really like the Higgs to be lighter than the Z or have mass of order the Z. And the Higgs is 125, so it's heavier than the Z. So it's a bit heavier than you expected from supersymmetry. And this is a major, the fact that the Higgs is heavier than that supersymmetry really wants is a major source of this residual tuning of 1 part in 100 that I talked about. All right. Okay, so the new supersymmetric particles only contribute to positional electroweak observables at one loop. Okay, so there are no tree-level corrections to positional electroweak in supersymmetric theories. And so that means that usually the positional electroweak constraints are just automatically satisfied in supersymmetric theories, provided the superpartners are, a few hundred GeV or heavier. Okay, so that's another really nice thing about supersymmetry. And again, I have nothing bad to say about that. Okay, that's just true. So here's, here are some of the reasons why, people really love supersymmetry. You probably have heard a lot of talks about supersymmetry and things like that. And here are the reasons why. Okay? Unfortunately, with the passage of time and additional data, some of these things don't look as good as they did 10 years ago. But yes, it's still a pretty interesting class of theories. So let me stop here and ask if there are any questions.
Yes, so Ganesh is asking what scale unification happens in supersymmetry?
Pardon?
At what scale unification happens in supersymmetry?
So the scale is 10 raised to 16 GeV. So this scale is 10 raised to 16.
And then Tessio is asking, can you repeat why the precise gauge coupling unification in the minimal supersymmetric standard model is not so relevant?
It's because there are always, there are going to be some new particles at the gut scale. There are going to be new particles with masses of order 10 raised to 16 GeV. Okay. Assuming there's, so I'm assuming there's a grand unified theory here. Okay. So if you have a grand unified theory here, there's going to be new particles with masses of order the gut scale. And they're going to, and when you're calculating the unification, you have to put those particles in the loop. So at one loop, those contribute to the matching. So you have to do a one loop matching calculation here. Okay. And those particles are going to contribute in the matching calculation, okay, at one loop. And some of those particles are going to be in pretty big representations, right? And so, in other words, there's a lot of particles there. It's not like you have one or two particles there. You have a lot of particles there. And so even though their effect is, kind of loop suppressed, because there are many of them, their contributions are not so small, okay? And when you put those in realistic models, what you find is that you usually don't get such a precise unification, okay? You get some distortion of this thing. Okay? And so it's a little bit of, it seems to be a little bit of an accident that you get something this precise.
Okay. So Anjali is asking you a religious question. Do you believe SUSY particles exist?
Well, there's two aspects to that question. One, the one question that the real question is, do SUSY particles exist at close to the weak scale or not? Right. That's if you're a physicist who cares about data, that's the most important question. I don't think SUSY particles exist at energies that the LHC can probe. That I do believe. That's my, I mean, I could be wrong. I mean, LHC could find supersymmetry tomorrow, okay? But if I had to make a guess, I would say they probably are not there at the energies that the LHC can probe. Whether they exist at energies that the next generation collider, some 100 TeV machine or something, can probe, I don't know. I'm agnostic. I'm not sure. Okay. Yeah. I think, we show, particle physicists show what we believe in by the amount of time we invest in a theory. Okay. So when I was a grad student and postdoc, before the LHC turned on, I invested a lot of time in supersymmetry, right? After the LHC turned on and didn't seem to have found superparticles, I haven't spent much time on supersymmetry, but yeah, okay. So that's my personal perspective.
Yeah. Okay. Yeah, I remember the days when before the LHC was turned on, people were saying that you find tens of gluinos, for instance.
Right. People thought that you turn on the machine and you'll find supersymmetry.
Yeah, that didn't happen.
Okay, I once told an experimentalist, you should expect that when you turn on the machine, you will see an amazing signal right away. And he said, I'm sure that's true because the machine won't have been calibrated properly.
But not even that happened. So Chacko, you have a few more minutes. Do you want to stop now or continue?
Let's just see, what do I have next? Okay, maybe let's stop here. Maybe this is a natural place to stop.
Okay. So talking about naturalness, yes, okay.
Yes.
It's a natural place. So, any other questions? Don't be shy. I know it was a long day, but don't be shy. You can also raise your hand if you want to talk and ask. Okay. Okay. So I don't see any further questions. So Chacko, thank you very much for this very nice lecture. And thank you all the students for participating. And I see you all tomorrow. Okay.
Right, see you guys. Bye.
Get some rest. Bye-bye.